is because I want to motivate, inspire all of you that there, because if you have heard in my introduction, I have a background in chemical engineering, and transformers is an umbrella term inside electrical engineering. So sort of a oxymoron for me. But here's the thing, it opens up your mind for interdisciplinary research and the kind of scope that you get for yourself and for your career building when you step into this kind of environment. So today's webinar is something that I do as a part of my day-to-day job. I have been at the core of building this, and I have experienced 100 million challenges. I still do. And I want to share all of that with you in hopes that you find this interesting. So let's begin. There's one more thing. Often when people from our side, from industry, come and give presentation to educational institutions, they often present numbers which don't reflect with the nation that you are representing. They often give you numbers from US or Europe or somewhere else. I want to give you something in the Indian context, because this is what is going to build your platform and interest from where you should be building your solutions, top to down or from bottom to up approach. So let's begin. A few years ago, about 7 years ago, India participated in the much publicized Paris Agreement part, quite, let me say, quite enthusiastically, okay? And then we also participated in something called Agenda 2030. If you don't know what Agenda 2030 is, it's actually a resolution which was passed from the United Nations in the last years. And it's a collection of 14 SDG, Sustainability, Development, and Governance goals. And it's a general understanding that all participating nations are committed to fulfill those SDG goals for the benefit in general of the whole society, economy, nation. One of those goals, SDG 9 in particular, says that it's the responsibility of each nation to provide clean, low cost, affordable, and good quality, uninterrupted energy to every household in that nation. Okay, this was the commitment. Keeping up with that commitment, today, India is one of the 5 largest producers. Actually, we stand on 5th rank when it comes to renewable energy production globally. In the last 7 years specifically, our installed generation capacity has increased from 275 gigawatts to approximately 400 gigawatts as of March last year. And this is a boost of more or less 45%. We have increased our inter-regional transmission capacity, which means we are working fast on interoperable operations, interconnected grids, and whatnot. So simply put, we have achieved quite 100% electrification. And you may not know most of these facts from the very famous ONOC policy, which is One Nation, One Grid policy of India. These are publicly available facts. But what this pretty picture doesn't tell you is that we are still fighting to manage uninterrupted power supply 24/7 by 365. Even today, unplanned downtime is one of the biggest challenges that we are facing. And while a lot of it comes, there are multiple reasons. It's not possible to summarize all of that in such a short session, but I just want to focus on the technology part of that. There are some governance and some other things as well. I'm sorry, there's a bit of noise, so if you're not using your microphone, could you please put it down?
Excuse me, Mr. Vinod Thomar, can you please mute yourself?
Oh, thank you. Thank you. So as I was saying, that one of the things which is causing this is the way utilities are managing these assets, especially the transmission and distribution side of assets. I don't know if you know this number or not, but right now in India, we have about 13 million installed distribution transformers across the nation. And the average global failure rate of transformers right now in India for public utilities is 10% annually, which is 10 times against the global average of 1 or 2%. That's how risky it is right now for public utilities. And there are many things, especially on the governance side, there are many things which are causing this. But let's focus on technology, as I said. So if you want to reflect this in terms of number, this means about 800 hours of downtime for a manufacturing facility every year annually. This means at least 80% of the organizations are affected with this kind of uninterrupted, unplanned downtime, unplanned outages. This means that the cost of repairing this downtime is more or less 10 times than that of the scheduled downtime cost, downtime planning cost. And in terms of money, we have been losing more or less 15 billion per year annually because of this, and especially in the manufacturing sector. You must have heard of smart grids. Smart grids have been at the core of all kinds of innovative technological policies in keeping up with the commitments of Agenda 2030, 2015, Paris Climate Agreement. We have been moving forward with improving our infrastructure.
Sorry to interrupt. Mr. PPJ, please mute yourself. I would request Dr. Shruti Chakraborty to please make me the host. I can mute the participants. Sorry for the interruptions. Yeah. Could you please make me the host from the participants list again?
Yes. Done.
Yeah, thank you. Thank you. Yeah, I can mute anyone now. Thank you.
Thank you. So as I was saying, I don't think I have to elaborate much into what smart grids are, particularly given the fact that all of you have a familiarity with this so far. We have incorporated a lot of things when moving forward in smart grids, but I don't know if it has caught your attention so far or not. But a major focus of the smart grid is on the transmission and distribution side of things. So although we have been incorporating a lot of generation resources into it, the major focus of smart grid action is on how are you managing this entire infrastructure, given the participation of so many things: alternative energy resources, active customer participation, battery storage, decentralization, and this and that. So the small answer is, and the simple answer is, that transformers are the key components of energy supply chain. So the entire focus and all of the money which goes into the entire scheduling and planning and management of all of this goes into what we know as transformer asset management. Okay. And we identify transformers as strategic components inside the grid, and we ensure that we have maximum availability, maximum reliability, maximum or at least optimal performance, extended life cycle, less failure, all of these things that you have read in books. Okay, through a collective action plan that we call as asset management. When it comes to asset management, SIGRE working group, there's a study committee, SIGRE A2, which basically focuses on transformers. And they published a technical brochure some time ago, the brochure 630, as it's seen on the screen. This focuses mostly on what we call as transformer intelligent condition monitoring. And they talk a lot about how you're supposed to do stuff for future technologies, as you can see on the screen right now for the smart grids, and how asset management in general is planned for a smart grid. But what you may notice right now in this picture is that there's a functional node inside this picture, the node which is in the center, and the one that is governing everything. This node is called condition monitoring. So at the end of the day, condition monitoring is a functional node which governs all kinds of asset management actions and plans and strategies inside the transformer industry. The same SIGRE committee came up with a list of features by the virtue of which you can define a well-fitted condition monitoring solution. And these are the conditions. You have to satisfy all 4 of them in order to call that as a suitable condition monitoring solution approach. You have to have a parameter which is easy to identify, which can be measured, which can be monitored. And every time you monitor or measure that parameter, you must have enough time between inspection and action by interpreting what the result is, by interpreting the course of action which follows, or whatever the consequence that follows because of that parameter. Case in point, some of you, or at least all of you who works in the high voltage side of things, or maybe familiar with transformer insulation degradation, must have heard of something called dissolved gas analysis. DGA is one of the key tests, routine tests performed in transformer industry, and is responsible for a lot of actions which goes behind the scenes in management and upkeep of these assets. So the point is, we have to identify something that we can test, something that we can monitor, something that we can measure, and we can interpret. And there has to be a suitable technique available in order to monitor that. I'll give you an interesting focal point here. My PhD was focused on moisture dynamics in power transformers. And one of the challenges we face in moisture dynamic, mathematical modeling of moisture dynamics, is that moisture in insulation paper of transformer is very hard to monitor because insulation paper is not easily accessible. So what do? We apply indirect methods such as mathematical models, we apply mass conservation models, we apply equilibrium charts or something of that sort in order to make an estimation of what could be the moisture content in paper. Okay, and when we are doing that, there is a very interesting parameter, water vapor pressure inside insulation paper matrix. There is no technique with which you can monitor this, at least non-invasive technique with which you can monitor this inside an operating transformer, thereby making moisture monitoring one of the most critical, one of the most challenging parts of condition monitoring transformers. This is just an example. The point at the end of the story is that your ultimate goal should be in producing condition information. With the help of, say, this moisture, you can tell what is the extent of degradation of insulation paper. You can tell if the mechanical and thermal strength and the dielectric strength has reduced or not. You can tell whether there is some sludge formation happening because of too much of paper charring out. You can tell a lot. And when you can tell all of these, when you can identify what kind of failure fault is happening, or you can identify what kind of failure mode is in action, you can take preventive actions. And with those preventive actions, you can solve a lot of problems, but more importantly, you can save a lot of money, which is what industries are all about. Okay. So take, for example, the picture that you see on the left side of your screen. You have some parameters. For example, ambient temperature is a parameter. Load current, the loading pattern of transformer, it's a parameter. Top oil temperature, it's a parameter. And you can measure top oil temperature, by the way. Okay. Furfural content, it's 2-furfural, 2FL, furfuraldehyde. You can monitor furfuraldehyde with laboratory testing as well. And so with the help of all of these parameters that you are collecting, sample that you're collecting, or online monitoring, you are gathering some information, which is then translated into useful knowledge, which at the end of the day tells you which action to take. As you can imagine, there are multiple spots inside a transformer which are very prone to failures. Most important zones are these tap changers and windings. Okay, and winding in particular is one of the most critical places because it's not accessible at all times. And every time if you have a fault in a winding, or you identify with some confidence that there's a fault in the winding, you have to make a reasonable explanation, techno-economical explanation to your asset manager. This is what happens in industry. I'm giving you a real life challenge which we face every day. We have to give a techno-economical justification. We have to show a confidence limit, and we have to confidently tell that this is the fault that is currently incepting, and this is how long it is going to take for this fault to convert into a failure mode. Okay, and at the end of the day, the transformer might stop working. So we need to take actions within this stipulated period of time, which is where my company steps in, or what we do in general steps in. As I was mentioning, there are a couple of secret working groups inside the A2 committee, specifically 2.8, 2.44 and 49, which work on transformer intelligent condition monitoring, and the other one helps you. The other one proposed a very fantastic technique. It's called asset indexing, transformer asset indexing. What is the point of this? As I have mentioned previously, you see, transformers are critical components inside a grid. So all you can do with online and offline testing, which comes under the umbrella of condition monitoring, is collect samples, gather data, gather a lot of data, and perhaps present them. But if I tell you that there is an actual engineer or a technician responsible for the upkeep of that transformer who is not very well learned on condition monitoring, or he is not an expert on condition monitoring, what do you think will happen? They keep on collecting data. And with the advent of online sensors, now you can imagine the influx of data generation right now. It's a huge amount. I don't know if you are aware of this or not, but typical online DGA sensors generate 4 times a day. They generate 4 readings in one day. So you can imagine the amount of data that is generated in one transformer for 1 year. And if you have a fleet of 500 or 1000 transformer, you can multiply. So my point is, when you have so much of data, when you have so much of information, you need to condense that, all of that, remove redundancies, and convert that into a useful information. Okay. So this is where the SIGRE committee stepped in, and they proposed what we call as the asset indexing strategy. Okay. So every asset indexing strategy has its own, let me say, requirement. The question is whether you are looking for repairing, refurbishment, or replacement of a transformer. It will ask you a certain set of questions, and based on those certain set of questions, you will be directed towards a certain algorithm, which will help you in transforming all of these qualitative data into a quantitative number. And with that number, you can tell what is the risk which is associated with your transformer right now, what is the reliability of your transformer right now, and what is the potential availability of this asset. How much time do you have before this transformer inevitably fails? I personally work in the field of transformer health indexing, and as it was previously mentioned, my entire focus is on transformer asset management. So with all of this information, I wanted to share with you some real case studies. I bring you 3 case studies today, and more can be arranged on request if you're interested, actually. But what happens is, in industries, depending upon the criticality of an asset, and I'd be taking questions at the end, so please, if you have questions, do feel free to put them in chat or however exchange. I'll be taking all of that in there. So back to what I was saying, in industries, when you are dealing with critical assets, and whether it's utility or it's a energy growth industry such as mining sector, mining industry, or anything, okay, at the end of the day, what you do generally as an asset manager is that you plug in a lot of online sensors to collect real-time data on condition monitoring. Okay, condition monitoring can be any of these parameters that you must have heard up until now. For example, dissolved gas analysis, as I previously mentioned, it could be a multiple gas sensor, single gas sensor. Oil humidity, relative saturation or relative humidity sensors, probes, which are available in market. Temperature sensors, optical fibers, temperature sensors, load, current, voltage measuring sensors, devices, IoT gateways for communication and whatnot. But what happens is, at the end of the day, you may be sitting on a huge mountain of information, not knowing what to do next. So here's a case study for all of you. This is a particular electric arc furnace transformer. I hope all of you know what is the electric arc furnace transformer, but just to give you a quick background, these are very strategic piece of asset equipments. And one of the basic requirements of these electric arc furnace transformers is within the steel industry. Okay, they are responsible for firing up the furnaces. They work on extremely high loading conditions, sometimes 1.5. The load unit could be 1.5, which means 150% loaded. Okay, and they are very, very stressed. These assets are very stressed and mostly operate throughout the day with a little, let me say, off cycle of about 30 minutes. So every time they have a full cycle, then they take it off for 30 minutes and then they recharge it again. You can imagine these are very stressful assets. So this is a particular electric arc furnace transformer, which was built in 1965, and this was analyzed last year, actually. What happened was the person responsible, the engineer responsible for upkeep of this transformer was doing what was told, the routine diagnostic testing with DGA and whatnot, and nothing unusual showed up. In fact, the DGA results showed zeros under all hydrocarbon gases. And you know that one of the key parameters which impacts the overall condition monitoring strategy, particularly for DGA, is when they read the TDCG, the total dissolved combustible gases. And the total dissolved combustible gases is a sum of hydrocarbon gases such as hydrogen, methane, ethane, ethylene, acetylene, carbon monoxide. And all of these gases were zero, which is funny, shouldn't happen. And because they were zero, the asset manager assumed that there's nothing wrong with this asset, and he kept on and he kept going on. What he didn't notice was the oil quality in terms of moisture, in terms of breakdown voltage, was degrading. It kept on degrading. So the failure of this asset in that production line would mean that there is huge production loss. Okay. So the manager of the plant, the manager of the unit, asked this question: how many more melts can I get before I have to shut it down? That's all they care about. They don't care about your asset. And as a condition monitoring expert, this is a challenge for you, because everything that you have read in textbooks goes out of the window, because in that moment you have to talk in terms of money. So how do you do that? How can you do that? We implemented a health index algorithm on this. For us, a health index algorithm, which was driven inside a machine learning framework, was basically condensing the typical condition monitoring data from that transformer, from dissolved gas analysis, oil quality parameters such as moisture content, breakdown voltage, interfacial tension, tan delta, and everything, into a number, a quantitative number, which was well defined inside a time scale. Which means if I tell you that the health index of your transformer near the end of 2009 was about 40%, it means that for an electric arc furnace transformer, it was performing well. Okay. And eventually in January, somewhere in January 2010, it started dropping, which is natural degradation, looking at the number of all the information that you have given. Oh, I forgot to mention, the zero data set was not used. The first thing that was done was we asked the lab to conduct another set of tests, the same test from somewhere else, because we were not convinced about the data integrity. Okay, and so what numbers we got, it was definitely not zero. And from the numbers that we got, we calculated the health index in that point of time. So what you see here is a transient series of health index over a certain period of time, about a year, of that particular transformer. And what we noticed is that the moisture kept on increasing. Although the degradation is not that much, the moisture kept on increasing. So every time they are, no matter how much filtration they are doing or how much degassing they are doing, the moisture is increasing. Definitely something is going on. And if it's not degradation, which is evident with the DGA, then it's something else. So health index told them, the way health index was moving, the dynamics told them that there is something serious going on, which is not related to the degradation. And given the current status, which is about 25% at that point of time, and it was alarming, it was really alarming. We decided that you should put a halt of the operation in a certain period of time, okay, and do a visual inspection of the asset. And upon visual inspection, it was identified that there was a gasket leak, which was causing the ambient moisture to ingress inside the transformer, thereby increasing the moisture of oil inside and showing all kinds of anomalies. There was a similar case study, again, electric arc furnace transformer for a steel industry, pretty similar scenario. What happened was we had larger set of data, and this was good quality data. I mean, the lab was not questionable. We had good quality data, and there was huge fluctuation. As you can see on the screen, the health index of that transformer over the years kept on fluctuating. And no matter how much they are filtering, they are degassing, the health index wouldn't stop fluctuating. And although these assets are highly stressful assets, this should not happen. So what was causing it? But looking at the trend of the health indexes, somewhere around, I think, the end of April, the mid of 2021, we decided that it's something else. It's not, the degradation is not the problem here. This is something else. So it turns out that they have been fixing the transformer here and there, and they have been doing some gas welding, because of which there was a huge amount of acetylene boost inside the oil, which was causing all kinds of fluctuations and abnormalities in the health index reading. So what do you understand from this? That no matter what you study in textbook on, this is the test that you should do, this is the rigid rule that you should apply, this is the recommendation you should provide in terms of numbers and time scales, at the end of the day, it's not just one thing. It's a collection of multiple strategies and multiple approaches, and not just simply based on best practices of condition monitoring. Does not mean good samples, taking good tests, repeatability, finding higher integrity labs, accredited places to work with. No, that's not condition monitoring. Condition monitoring is the ability to make an assessment of your asset based on multiple things, not just on chemical tests or electrical tests or mechanical tests or acoustic vibrations or whatever. No. It is also the ability to make a call of judgment when the risk is high, when the reliability is low, and how much time one has in order to prioritize their actions. And with the help of this kind of information, you can make short to mid-term budgets, which are one of the most critical parts of any asset management enterprise across any industry, not just transformers, even if you go to other process industries. And transformers is just one part. Similar things happens with switch gears, circuit breakers, cables. Critical, very critical. There are very few things that we can monitor in cables. And imagine if you have a fleet. So this is my last case study for you, and we'll be concluding the webinar, the presentation quickly. Imagine if you have a fleet of transformers. I say if you have a fleet of 500 transformers, and let me say that you have a condition monitoring protocol in practice right now. You have a asset management protocol in practice right now. Here's what happened, and this is a real life example. National Grid, UK, has what it calls a risk management protocol in practice. What they do is they look at their condition monitoring protocols, algorithms based on typical condition monitoring data from chemical testing, mechanical testing, thermal testing, electrical testing, and whatnot. And then they categorize their assets in 3 categories: low risk, medium risk, high risk. But the question is, what if you have multiple assets in high risk area? How do you prioritize? How do you rank them? That this is the asset that I have to get into. It's a very qualitative information. It's not a quantitative number. How do you prioritize? So one of the best practices of condition monitoring is when you apply intelligent computational intelligence into transforming this data into actionable information, which helps you in such kind of actions. For example, this is a fleet. This is a part of a fleet. To be very honest, this is a part of a fleet. As you can see, these are power transformers, and this is well, I cannot tell you a lot of things because of professional commitments, but I can tell you this. This is one of an Israeli utility, and you know how Israelis are with their data and with their assets and security and whatnot. So this is one of one of the famous Israeli utilities, and this is a part of their fleet. And what you see here are the health indexes of their transformers, which were rated between 20 and 50 MVA. What they were doing is typical routine testing, conducting DJ once or twice a year, depending upon the current situation. Okay, And that's it. And so if any transformer fails, that means there is huge loss for the utility on social as well as financial parts. There's going to be investment is going to be hampered. So their question is, how do I rank this? How do I tell that this is a bunch of my assets which are under high risk area. I have a couple of 4 or 5 assets which are in high risk area, but how do I rank them? Health indexing came to this, their saving. With this kind of strategy, what they did is, again, transformed typical condition monitoring data into a quantitative number, which was good enough for them to be, and it was well defined on a time scale, which was good enough for them to identify, okay, so the one asset which has a health index of about 25% requires urgent intervention than the one which has 60%. And I want to mention one last thing here. In doing this, in building this algorithm or implementing this algorithm, age of transformer, which all of you must have heard, age of asset, life, service lifetime of asset, critical lifetime of asset, remaining life, age is not a fact. Something which is standing there for 70 years is probably going to stand there for a couple more if nothing extreme happens. Something which has been installed very new, it's 5 years, less than 5 years, might crumble if you're not paying attention. So age is never the guarantor. It's not the marker. The marker is condition monitoring data. So as I was saying, in all of this, what came to our rescue is machine learning. Now, I don't have to explain this flow chart in front of you because it's a very, let me say, textbookish kind of thing. And all of you must have seen it somewhere. But what I want to mention in this point here is that it doesn't matter whether you are using this approach, the AI ML approach, or traditional statistical approach, or traditional mathematical equation approach, or whatever. The question is big data or better data. That's what you should ask. All of this is possible. This entire machine learning algorithm is possible if you look at the yes or no's. The question is, do you have enough data? The ultimate question is, do you have enough data? And the data is so complicated. Is the data so complicated that a human cannot naturally make, cannot recognize the patterns or cannot make inferences? If that's the case, then you should probably go on with artificial or machine learning algorithms. That's the basic question everybody asks. But I want to take you a step further. Don't ask this. Ask whether you want a good data or a big data. And I want you to take this with yourself as a homework and think about it, given the kind of complex industry that we are catering. Okay. So in conclusion, the best practices of transformer condition monitoring right now, I don't know if you're aware of this or not, 60% of our market share, the transformer condition monitoring market, is governed or dominated by hardware. They have all kinds of hardware, online sensors and monitors and devices in the market right now. And about 30% of it is governed by so-called software companies, which are providing integrated software solutions to transform that data into actionable information using all kinds of methods, not just health indexing. Okay, some do fault classification, simply fault classification. Some do remaining life assessment. All of these are different things, by the way, for industries. So what is the conclusion of all of this? What have we learned from all of this? That if we want to digitalize the best practices of condition monitoring and cater to industrial problems and produce a cost-effective, energy-efficient solution, then we have to be on this pentagon. The first thing that we have to ensure is the reliability of these solutions. And as critical as it may be for us in defining the whole reliability aspect, because as an industry insider, I can tell you, we often argue a lot about what reliability actually is. And it's very different from accuracy or precision, which you study in stats. Okay. So the first thing we have to ensure is what is reliability for this? How reliable are this? Is this a good prediction or an evil prediction? Then we have to incorporate the scope of data. into making decisions. Instead of rigid rules, we have to allow data to make path for decisions. And when you are introducing data, there's an old saying that all data comes from bias, but not all bias comes from data. Sometimes it comes from other places. And this is fact. Interesting story. I have been working on a little project, which is called Humans and Ronin, where I am testing the bias of condition monitoring experts in transformer industry by giving them a piece of a certain algorithm and testing their inputs against what a typical machine learning algorithm would produce. And you'd be surprised if I show you the results. So bias is a very important part of digitalization practices right now. As I mentioned previously, data quality, of course. I said a few slides ago, big data or better data. It's not about the amount, it's about the quality. If you have a negatively skewed data, which means you have a data quality, a huge data group, okay, with all faulty transformers or all faulty cases, then you are probably going to build an algorithm which is only suitable for faulty transformers. If you have a data set which is only good for good transformers, they have very good data, excellent transformer life, etc., then you are probably going to build it for a certain category, which means every time you are testing it for a transformer which is outside of that category, you are making an overfitting mistake. Not acceptable for industry. And in all of this, the biggest challenge that I face, given the current, let me say, the industrial wind towards sustainability and resilient solutions, managing decarbonization in condition monitoring. People don't understand where decarbonization plays a role in condition monitoring. Do you think carbonization only means CO2 emitting materials? No, carbon footprints also comes from humans. So all these carbon footprints that we are leaving while managing the so-called effective condition monitoring of assets and effective asset management for smart grids is actually going to a waste, because we are not nowhere near sustainability. We are not keeping up with reliability. We are not resilient. Okay. And so my major challenge is to find a balance in this pentagon. And with that, ladies and gentlemen, I want to conclude this webinar. I'm sure you have a lot of questions, so I'll be taking them. And yeah, that's it.
Thank you, Dr. Chakraborty. It was such an engaging talk. I would request all the participants to post their questions in the chat box. Meanwhile, I would ask you to share your personal experience regarding the career prospects that you chose, the interdisciplinary pathway that you chose, switching from being a graduate in chemical engineering and starting a startup that is primarily based in the electrical or power domain. How was it? What was the experience? And I think the participants would benefit from that. So I would like you to, request you to
sure,
share your thoughts.
That's a wonderful. You asked a very personal thing, and it's something very close to my heart, actually.
Meanwhile, participants can pose their questions. You can share your, journey.
Yeah. So I never thought that I'll come in this sector, honestly. And I came by accident, to be very honest. I won an internship for Crompton Greaves in 2011, and I was posted in their global R&D center in Mumbai. And I was responsible for some dielectric insulation related work. Up until that point, and I was in my master's program in that moment, I was doing my MTech. Up until that point, I used to imagine transformers, electrical transformers, as you have read the definition in the textbooks, is an electrostatic devices which converts voltage levels and transmits energy over long distances over a static frequency or whatever. In that moment, I realized transformers are not just electrostatic devices. They are thermodynamically closed systems where the inherent conditions, thermodynamic conditions on temperature and pressure are potent enough to cause everything that I have studied in chemical engineering: heat transfer, fluid flow, mass conservation, chemical reaction. As a part of chemical engineering curriculum, we study equipment designs, the suitability of equipments. And in that, we study the thermal and mechanical suitability of these equipments for a certain process. That was the first moment I realized moisture dynamics is not just electrical problem. It's not as simple as just fix second law of diffusion. It's more critical than that. And that was the moment I fell in love with this field. And it's been 10 years, it's been more than that. It's been 13 years, and I'm not over it. I don't think I'll ever be over it. So when I was asked to choose my master's topic, I chose moisture dynamics, actually. Well, in that moment, I was doing something else. I was doing aging characterization of insulation components. But eventually, and that was the moment I realized the importance of CFD simulations, the numerical modeling in improving the existing models for monitoring and all these methodologies. So eventually, when I finished my PhD, I was certain. In my PhD as well, I was very certain, and if I have to stay, I'm going to stay in this field and gain knowledge. And when I have to build a career, I want to stay in this field and work as hard as it may take. And that is where I met some of these wonderful people who are now my co-founders through mutual friends, actually, who gave me this space to build this company, which is entirely focused on what I have studied in college, what I have studied in my PhD, and now catering to these real-time challenges and trying to produce solutions, which is, I fail 100 times a day. That's fine. You don't have to necessarily be like, I have to succeed 100% in order to build something. No, I have failed for more than a year before I actually built this up. So I hope you find motivation in this. I see a question here. In the Pentagon, isn't debiasing incorrect? Because bias comes from known physical laws, and debiasing should not override contribution of physical laws. Rather, it should provide a compromise between bias and information available for data. You would be surprised how bias comes from. It doesn't come from physical laws on. As I was mentioning about this little project, okay, one of the things I asked was, there is this transformer, we have this data available. Well, how would you like to rate the risk and reliability of this? This is the standard IEEE method for, I think all of you know, or if you do not know, there's a standard IEEE C57.104, which helps you in fault classification, and 54 point something, I forgot, which helps you in interpreting the results of DGA. And with the help of this interpretation, you can actually do fault classification. This is law, right? This is rule. This is rigid based systems. These laws are based on physical laws, based on how the degradation kinetics works and how a failure mode eventually propagates into bigger issues. You'd be very surprised. Two people who are senior most experts gave polar opposite results, understanding from the same data. And the reason is experience. Their experience in managing fault identification and fault classification based on that kind of data. So debiasing is not as easy or black and white as you may imagine. There are other things as well which come into factor. Okay, and sometimes these factors are experiences of the said condition monitoring experts and their demographic. You may not, I don't know if you're aware of this or not, but you may not believe this. A condition monitoring expert who has been catering only to Middle East has entirely different experience from the one who is catering to North America and Canada. So looking at the same data, both of them made polar opposite predictions. Same data. So I think that should sort of help you clear up things, and it should provide a compromise. Well, the compromise for industry, the compromise is where money comes from. Okay, we have to make a workable compromise from where, how much we can debias and how much that is acceptable by industry standards, because sometimes no matter what you write inside a standard protocol, in reality, transformer is working, behaving differently than that. So I hope that answers your question. If not, I'd be happy to take it up personally. Digital twin built from SFR, DGA, leakage current, signature analysis rather than to simply have. Okay, good question. Very good question. Balaji Lakshmi Narayan. Balaji Lakshmi Narayan asked a very fantastic question. Digital twin. I am the head of data analytics for one of the SIGRE committees, which is working on transformer digital twins right now. So this is a question which is very close to what I do right now. You see, when it comes to building digital twins, when it comes to building data-driven stuff, you know what is the capital? Data. And you know what restricts it? Availability, consistency, and timeliness of that data. You know, these hardwares that they are so circulating in the market, they come with a lifespan, right? So which means when the transformer, when this monitoring sensor is out, when it has finished its lifetime, until and unless you are putting a new sensor back onto that transformer, there's a gap. And whatever this new sensor is monitoring from the day one of its activity, is this consistent, coherent with what the last one monitored? So availability of good data, okay, SFR was mentioned here, so I'll particularly talk about that. SFRA is done once or twice in the entire lifetime of a transformer. Not the kind of data that's needed. It's not good. Okay, leakage current, signature analysis. Leakage currents and signature analysis, particularly if you are talking in terms of vibrations, or even if you are talking in terms of electrical testing, is a FAT. It's a factory action test. Okay, and a factory test data is not enough. You need field data. DGA is a good field data. So you have to make sure that when you are building a digital twin, you have access to data which is continuous, which is not sporadic, okay, which has consistency, which has timeliness, and that is easy to collect. What happens? You go to a client and he says that, oh, listen, I don't have SFRA. Can you still build a digital twin for me? And you would say, no, that's not how it works. So you have to make sure that you build a solution which is based on what is available, what is easily available, because cost of testing hinders all project costs in the industry. Always remember. Partial discharge from UHF methods, same. Partial discharges are not always available. For cables, partial discharges are fantastic. For transformers, not so much. And particularly if you're talking about main tags. So yeah, my answer extends to the same point. So I think, simply put, pick data which is easily available rather than complicated data which is tested once in a lifetime or very rarely, only when it is asked.
I hope
these things in the textbooks.
I hope this answer your question, Balaji. If not, you can unmute yourself and ask for further clarification if you have some more doubts, questions.
I have just one question more. So how about using polypropylene as winding insulation rather than craft? Because polypropylene avoids moisture ingress, and therefore it can be better. Because people are preferring it nowadays, right?
Yeah, people are preferring. But here's the thing: behind every application, we have to basically test three things: availability, cost, and long time material characterization. So these are the three things which more or less decides which material is good enough to be put inside a transformer as insulation. Because if you remember some time ago, and even I worked on this some time ago, ferrofluids were pretty much in they were pretty much the trend. I don't know if you have read about ferrofluids or not. I did ferrofluid testing, aging kinetics of ferrofluids. You'd be very surprised how much time it takes for breakthrough. 19 minutes. In accelerated aging condition, ferrofluid breaks in 19 minutes. Dotted nomics paper implemented in ferrofluids, which are very common in transformer windings. So I think the answer to your question is, of course, that can be done. And I think it's currently in the research stage. And more than anything, with all the focus which is on high temperature superconducting transformers, it's quite on the research stage. And what we are currently trying to do is find a focal point between availability, cost, and long-term characterization of polypropylene material. And we have not been able to find that optimal balance as of now.
Okay.
Insulation stayed properly in presence of dynamic factors such as moisture migration, influence of low frequency noise and dielectric response such as PDC. Okay, this is an entirely different thing. I don't think we have that much time left. We have just 4 minutes, but I'll still try. Aniket asked, how can we accurately characterize insulation state properly in presence of dynamic factors such as moisture migration and influence of low frequency noise in dielectric response analysis such as PDC? Okay, so as you are probably aware, moisture migration can not only be monitored through these dielectric response methods or frequency response method. There are other methods available as well. One of the most famous methods, and although it's a bit indirect, is the KFT, Carl Fisher titration, and it's governed by, I think, 61840 standard, IEC standard. You can read about how to do it there. But my point is that every time we have issues of this sort, where sometimes we and not just with moisture, I can tell you, we have faced similar issues with DGA, dissolved gas analysis as well. Hydrogen signatures were off the chart, and every time hydrogen is high, it's going off the chart, people would say partial discharges. Every time we have issues like this, we have noises or the charts are sort of unreliable, we always go for a secondary method. For in this case, as I was mentioning, dielectric response analysis is one method. The other one is relative saturation measurement. Okay, it's relatively it has relatively lesser noise signatures as compared to this, because it focuses on something different. It focuses on the molecular level rather than on the macroscopic level. Okay, and from there we sort of make an assessment of whether this reading of moisture measurement is right or not. And you are right, moisture is quite dynamic, but it's not as dynamic as you would imagine. And moisture is dynamic mostly when the loading temperature, I mean the load patterns are fluctuate, and that happens in very small portion of the fleet. That doesn't happen to every transformer. It happens to the distribution transformers, which are at the lower end. Okay, so in those cases, we rely more on relative saturation as a field study. We rather rely on relative saturation signatures, relative saturation charts rather than these. So I hope that answers your question.
So with this, I would end this session, and I would end this with a last question from my side. Yeah. That I would like you to throw some light on the specific computational techniques that you involved in addressing the conditioning monitoring of the transformers. I think the specific computational techniques were not talked about in the presentation.
Okay. So no, I didn't put any company stuff in here because I wanted to keep it rather general for everybody. But as far as what my company does, I was a part of building this algorithm, which is how should I put it, supervised multivariate regression model.
Okay,
is that easy enough to understand?
Okay. Yeah. Okay.
Okay, so it's a self-stacked algorithm. Okay, there are multiple things working inside the framework. I cannot open everything, but I'll say this. This is a supervised algorithm, and the intention behind this is to find a relationship between seemingly unrelated parameters rather than fault classification and all of that stuff. But you can do the same with other computational methods such as fuzzy logic. You have SVM, you have neural nets, you have deep learning methods, you have hybrid models as well. So apart from the simulation part, the CFD part, these are also some of the methods that you can apply. Evolutionary algorithms, etc. Particle swarm optimization.
Yeah.
Depending upon the cause, of course.
So basically more of a learned machine learning
Yeah, the
algorithm, or
machine
right?
learning algorithm.
Yeah,
Yes,
which is
yes,
a more
yes,
learned on the system-specific behavior, I would say.
yes, yes.
Yeah, so with this, I would like to close the session for today, and it's our pleasure to have you on board, Dr. Shruti Chakraborty, as the speaker of the event. And in that regards, please accept a virtual token of appreciation from us.
Oh, thank you.
Yeah.
Thank you.
Thank you, everyone who have joined together at this webinar. We would definitely have you for further sessions. And thank you all. Thank you, the participants and our mentor and our faculty advisor, Dr. Alok Ranjan Verma, and our mentor, Dr. Nandini Gupta, for making this event a success. Thank you. Thank you, everyone.
Thank you so much. Thank you. Thank you for having me as well. Thank you. Bye-bye. Have a nice day.